Okay, ladies and gentlemen, today we're doing section 9.5. We're only going to be multiplying radical expressions today. We'll be doing the note sheet page 1 and the first two problems on the top of page 2. And notice in the directions, it says assume all variables are positive. And what that means is after we extract all roots, we will never need any absolute values, symbols on the outside like we needed previous in 9.4. I'd like you to give these four problems a try quick, and I'll be back with the answers in a minute. Okay, number one, we want to extract perfect squares because this is a square root. So I'm going to look at this as 4 times perfect square 54. Well, that comes from what? 9 times 6, right? And because 9 is a perfect square, that perfect square of 9, which is 3, comes out. That's going to multiply with the 4. And that 6 has to stay underneath, and because these two numbers are both on the outside, I multiply them together and get 12 root 6 for that first answer, okay? You're going to see a couple different methods that I use here. Small numbers like number 1 and 2, I can see perfect squares really easy. So what I want to do is I want to see that as I know 12 is 4 times 3 for a perfect square, and whenever I run into variables, if it's an even root, I want an even number of powers on that. So that's times an x squared. And y to the fifth is odd, so I'm going to break that apart to a y to the fourth times a y. Then I'm going to come back. I know these are all perfect squares, and I know the perfect square of 4 is 2. I know the square root of x squared is x, and I know the square root of y to the fourth is y squared, and 3 is not a perfect square, so it stays underneath the root, and y to the first is not a perfect square, so it stays underneath the root, and I get right there. Now notice number 3 is a cubed root now, and number 3 for me, 128 is a pretty big number. So what I like to do a lot of times is I like to prime factorize these, and I'm a very small thinker because I know 2 goes into 128 64 times, excuse me, and because that's even, I know 2 goes into 64 32 times, and I know 2 goes into 32 16 times, and I know 2 goes into 16 8 times, and I see a perfect cube here. So what that means is, because this is a cubed root on the outside, any three of the same numbers on the outside, 2 times 2 times 2 is 8, so that's 3 2's underneath there. So really what I get is I'm looking at the cubed root 8 times 3 to the fourth, and I'm just showing how, because that's an odd power, or excuse me, 4 is an even power, so I need 3 of these 3's to come out, and that's not a 3, that's a 2, excuse me. So I know the cubed root of 8 is 2, and I know 3 of these are going to come out for a 2, and one of those 4 2's stays underneath, and I know 2 times 2 is 4. Cubed root 2 would be my simplified answer of that one. Okay, I don't see the perfect cubes as fast. Some people might have seen 64 times 2 for your perfect cube of 4 to come out. Number 4, again, it's another odd root, and this one I'm going to tackle odd number, so I know 8 times 2, 8's a perfect cube, and now because this is an even number underneath here, I want to see an odd exponent, so I'm going to see times x to the third times x, so there's still 4 of them down there, and I know 3 will divide evenly into that, so I'm going to leave that as a y to the sixth, okay? So I know the cubed root of 8 is 2, and I know the cubed root of 2, there's none, so it stays there, so cube, these are all coming out. The cubed root of x cubed is x, and the cubed root of x to the sixth is actually, or y to the sixth is actually y squared. And what stays under that cube root is that 2 and that x. And that's the 4 warm-up problems, okay? Be back in a minute. Okay, these first two examples, when I multiply square root expressions or even cubed root expressions, I have options, okay? There's always 2 ways to skin a cat. The first method I prefer, because I know the square root of 4 is 2 times the square root of 9 I know is 3, and 2 times 3 is 6. And underneath that, I know the square root of 16 is 4 times, I know the square root of 25 is 5, because these are two perfect squares. 4 times 5 is 20. Or if I prefer to work with big numbers, which I don't, I can take the square root of 4 times the square root of 9, and because both of those are underneath the exact same indexed root, it's really 4 times 9, and I know 4 times 9 underneath that root is 36, and I know the square root of 36 is 6. And the same here, I know 16 times 25 underneath that root, that gives me 400, and I know the square root of 400 is 20. So we have options. So what I'm going to do is I'm going to write these multiplication properties here on my board for you on the right hand side so we can reference them through all the next, I think it's 11 it's actually 11 examples. 2 of them are marked wrong. Okay, you might want to pause this video here for a second. Underneath the multiplication properties here, I got 3 rules for you. I call them belly button rules, innies and outies, but rule number 1, numbers that are under radicals can be multiplied together, meaning I can take 8 times 32 and make a new square root, okay? Number 2, numbers outside radicals can be multiplied together. You're going to see how that comes out over here when I'm multiplying 2 radicals together. Rule number 3, the big one, do not multiply outside numbers and inside numbers. Outies do not mix with innies, okay? Outies with outies, innies with innies. What this means is over here, well, I can multiply the 8 and the 32, but that gives me a big number, and I don't like to use big numbers. So what I'm going to do is I'm going to see the square root of 8 is the square root of 4 times 2. And that's times, I know 32 comes from 16 times 2. So I can simplify this 8 to 2 square root 2 times, I can simplify this one to, oh, forgot to write my 4 first, so I'll squeak it in there, 4 square root 2. Now, numbers outside can be multiplied. So that means 4 times 2 gives me 8. And numbers underneath the radicals can be multiplied. 2 times 2 is 4. Oh, 4 is a perfect square again. So that's 8 times 2, or 16. Might have seen that perfect square because there's nothing left in the root if you'd have multiplied those together. Okay, when I look at number 2, 5 square root 3 squared. Well, that's 5 square root 3 times 5 square root 3. Multiply outside numbers. 5 times 5 is 25 times multiply inside numbers. You're going to determine shortcuts here. 3 times 3 is 9. Oh, that's a perfect square. Big shock, 2 of the same numbers underneath. It's really 25 times 3, or 75. Okay? And I'm going to pause this here, and I'm going to write some new examples. Okay, next 4 examples. What makes teaching radicals so much fun to teach is there's so many ways to do them. When I look at number 2, first thing that comes to my mind, they're all small numbers. I'm going to multiply my outside numbers to get 6. And then I'm going to multiply my inside numbers. 2 times 6 is 12. And I know x to the 3rd times x gives me x to the 4th. Then I got to come back and I got to think, there's a perfect square in there. That's 6 times 4 times 3 times x to the 4th. Okay, well, I know the square root of 4 is 2, so that's really going to give me 6 times 2, because that's a perfect square, times, that's a perfect square, gives me an x squared, and that square root of 3 stays underneath. Everything on the outside now, I would multiply together and make sure there are no perfect squares left underneath that root. Number 14, because I don't want to take 14 times 35. That's too big of a number for me. So I look at this one and I see that's 2 times 7 times the square root of, I see 5 times 7. Okay, well now notice if I multiply these together and I wrote it in one stretch, this is a lot of mental math here, it's 2 times 5 times 7 squared if I prime factorized it. And because this is a square root, this is 7, oh, that's 49. So that's a perfect square of 7 that comes out. And there's no perfect squares in 2 or 5, so I just multiply them together to call it 7 square roots of 10. When I look over here at number 5, I'm going to take my outside numbers quick. I'm going to multiply those. and I get 6. Well, then I look at this, and I see this is 6 times 2 for 12 because my eye's dialed in on this times square root 6 over here because I'm comparing, oh, there's a 6 in there. So if I multiply these outside numbers and kind of jump, that's 2 times 6 squared. Oh, perfect square. There's a 6 that comes out because 6 squared is 36. Well, that gives me a 6 times a 6 on the outside. Square root 2. Oh, that's 36 square root 2. Okay. Number six jumps me to cubes. Oh, so now I got to think prime factorized because I don't have all my perfect cubes memorized really well. Well, I see this as the cubed root of 3 times 3, okay, times, this is a cube, oh, I do know, that's a cube. 8 times 3 gives me 24. So when I itemize this out, this is really a cubed root of 8. When I multiply all this stuff underneath, it's really 8 times 3 cubed because there's 1, 2, 3 threes underneath there. And when I look at this, I'm like, oh, cubed root of 8, I know what that is. That's 2. And the cubed root of 3 cubed, oh, that's just 3. And because those are both on the outside and there's nothing left underneath there because those are both perfect cubes, I'm just left with a 6. And why don't you give the next couple here a try as I am paused and see if you get them right. Okay, well, I understand I jump around here a little bit, but method I typically use is I like prime factorizing method best. And I look at this 18. 18 comes from 2 times 9, and that's 3 times 3. So when I'm multiplying numbers, I'm multiplying the prime factors of all the numbers underneath here. Okay, so then I'm going to see this is going to be a cubed root of 2 times 3 cubed. That takes care of all my numbers. And I know x squared times x to the 5th is times x to the 7th. But I know 3 doesn't go evenly into x to the 7th. So I want to break that down a little bit. I'm going to make that x to the 6th times x because I know 3 will go in there evenly. Okay, so now when I look, 2 is not a perfect cube. 3 cubed, that's a perfect cube. A 3 comes out, perfect cube. I know x to the 6th, the cubed root of x to the 6th, hey, that's x squared, so that's a perfect cube. And the last 2 that are there, here's a cube. I'm left with 2 times x. And got to be really careful that you don't really nest these together. Mine kind of looks, you want to make sure any exponent on the outside is separated from what's in the saddle. Okay, so my prime factorization method is typically what I do. I see this, I see that as 3 times 9, and I see this as a 3 times 3. Okay, so what I would do is all mental math here. I would bring this down. These are still square roots. 1, 2, 3. There's 4 3s when I get rid of them all. So that's 3 to the 4th power. And then that's times y squared is y cubed. Well, the square root of 3 to the 4th, well, really in my mind, I know there's a 3 squared that comes out, but you kind of are seeing 3 squared times y squared times y. So when I pull them out, I can see 3 times y, and that y stays under. All those underlined ones are perfect squares, which gives me 9y square root y. And when I come down here to number 9, just remember that is 3 square root 2x to the 3rd y times 3 square root 2x cubed y. And in this case, I'm seeing 3 times 3 is 9. And they're small numbers. I know that's going to give me a 4. X cubed, that gives me an x to the, 6th. Y, that gives me a y squared. And now perfect square, perfect square, perfect square. So the 9 is on the outside, times square root of 4 is 2, times the square root of x to the 6th, that's x to the 3rd, times square root of y squared is y. Everything underneath was a perfect square. 9 times 2 is 18. x to the third y if you did them right. All I'm going to do is I'm going to hit pause and I'm going to write the answers for the last two challenge problems on the other side and see if you get them right. Okay, these last two challenge problems, not all that challenging, but we'll see what you think. First thing I'm going to do is I'm going to multiply my outside business. So I have 12a. Then, in my mind, I prime factorize that. Well, I don't need to totally prime factorize it. I know that's 2 times 9, and I know 9's a perfect square. 3 is not a perfect square, so I'm going to leave that number underneath. But then I'm going to take these and multiply them together and see that's a to the third times a squared. That's a to the fifth. So I want to see that as a to the fourth times a, so I can take the perfect squares out. So I have 12a, and 9's a perfect square, so that's times 3. A to the fourth is a perfect square, so that's times a squared. And what's left underneath here, 2 times 3 is 6, and there's an a, and then I'm going to multiply everything that's left underneath here. Well, that's going to be what? 36a to the third square root 6a. Okay? If you're nailing these couple out here, you're doing just fine and you're right where you need to be. Here I have nothing outside to multiply. So what I do is I see 5 as prime, and I see times 5 times 2. I organize my numbers underneath. Here's my 10, here's my 5. X to the third, that's times x to the sixth. Y times y, or y to the fourth, that's y to the fifth. So as I'm moving along here, as I'm coming underneath, in my head, I know that's 5 times 5. Well, I'm seeing these two 5s right here actually as 5 squared. And this y, because I know it's an even root, I want to make sure I can see a perfect square, which is a 4 times y, so I still have y to the fifth. Then I come back and I pull out my perfect squares. I know the square root of 5 squared is 5, that's a perfect square. I know x to the sixth is a perfect square of x to the third. I know y to the fourth is a perfect square of y squared. And 2 is not and y is not, so 2y stays underneath my radical symbol. And that's as far as we're going to go today. You can give a couple of the problems on your homework assignment a try if you want. If not, tomorrow we are picking up. We're going to add and subtract them. Much more complicated, so you need to make sure you have your multiplying down today. Talk to you tomorrow.